direct variation. All right? So let's see how the best way for us to proceed is. Let me start out with an example of a function that we have been looking at, and let's look at the notation. And remember, if I start out with, say, the function f such that, well, suppose I were to write y is equal to 1/2 x plus 3. All right? This is one way in which we have learned how to write a function, to describe a function, to write the rule for a function. Another way is to say what? The function f such that, in which we then use this f of x notation, is that right? In which I can say what? F of x is equal to what? 1/2 x plus 3. And then in fact we had a third way in which we can write it. The function f such that x is mapped into 1/2 x plus 3. Is that right? In which we have any one of these three methods now by which we can write the rule for a function, or in which we can describe a function. Okay? Let's come over to our coordinate system and actually make a graph of this function. And let's see now, we're looking at y equals 1/2 x plus 3. What's the y-intercept? 3, 1, 2, 3. And what's the slope number? 1/2. So let's decide to come out 1, 2, 3, 4. And then let's decide to rise 2. And through those 2 points, is that right? We have a line. And let me indicate that line right here by this line passing through those 2 points. And now notice as soon as I put the arrowheads on it, we have this line which goes on infinitely in both directions. And let me write a formula right in here for this function, okay? In which if I'm using, notice here now on the y-axis I have f of x. So I think you will allow me to say f of x is equal to, and what's the formula that I'd like to write here, Steve? 1/2 x plus 3. And of course its graph is a line. So what kind of function do we call this? What name do we give this function, Ron?
Linear.
This is called a linear function. A linear function, all right? And this is just a special case of a linear function. What would then be the general case of a linear function? Instead of calling this a y-intercept of 3 and a slope number of 1/2, perhaps remember the symbols that we have been using. We've been talking about a y-intercept of b and a slope number of m. So how may we then write this function? And David says,
F of
all right,
A
f of x is equal to,
AX plus N.
all right, let's see now. The letters that I think we've been using for slope is m, and the y-intercept is b. So Brenda says f of x is equal to mx plus b, all right? And this is what we think of as the general case of a linear function. Now what I'd like to do today is to look at a number of examples, special cases of a linear function, all right? And then in fact, these are problems, these are examples that we have been looking at before, but we've never thought of them in terms of a function. We haven't used that word and that notation. Let's come over here to another coordinate system, and for example, suppose I were to take a y-intercept of 4, 1, 2, 3, 4, and a line parallel to the x-axis, and let's say that our line is this one right here. And of course, what then is the formula for this function that we have listed, that we have written here? Anyone can come up with a formula for this? We have a y-intercept of what? 4. Of 4, and what's the slope number of this line? The slope number is 0, and so what then is the equation for this line? And anyone?
Y is equal to 4.
Chip? Y is equal to 4. All right, y is equal to 4. Now notice here we have a function in which every element is mapped into the constant number of 4. So if we had to give a name to this particular function, what name do you think we could give it? What would be a name that we could give this function in which every element is mapped into some constant here? And Sally says, a constant function. Okay, this is going to be a constant function in which every element from our domain is mapped into one and only one element in our range, okay, which in this case is going to be the number 4. Now, again, let's write this in terms of our special case, and instead of having the number 4 here for a y-intercept, let's decide to call it b, and our slope number is 0. So what then is a formula that I may write right in here for a constant function? What can we say? Y is equal to, and Ken?
B.
Y is equal to b, in which we think in terms of this is our y-intercept, okay? So here's a special case of a linear function in which it happens to be a line which is parallel to the x-axis, and we call that a constant function. Okay? Let's come over here and look at a third example. And in this case, let me have a point through the origin, a line passing through the origin, and a slope number of 1. Okay, so let's decide to come out here, let's say 1, 2, 3, 4, 5, and rise 1, 2, 3, 4, 5. And I think you will agree that through these 2 points we have a line which is going to pass through the origin, and let's see who can give us a name for this particular line that we have here. Notice here we have f of x again, and what then is a formula that I may write for this particular function? This is one which we have been looking at. What's our y-intercept? The y-intercept is 0. What's the slope number? 1. So what then is an equation for this line, Bob?
Y is equal to x.
Y is equal to x. Since I have here on this coordinate system f of x, let me use f of x is equal to x. All right? Now, let's go back and think about our real numbers for a minute, in which, if you recall, a plus 0 is equal to a. And what name did we call that number 0 in terms of addition, Ken?
Identity.
An identity element, all right, in which we start out with some element a and add 0 to it, and it gives us the number a back. And of course, in terms of multiplication, a times 1 is a, so we call the number 1 what? An identity element. Now here we have, think of this as a function in which, think of your function box, for example, in which you put the element x in, and you push the button, and what element comes back? The same element, what? If I put the number x in, right, and I push the button, what element pops out of our box, out of our function box? X itself, all right? So what name do you think we might want to give this particular function, Chuck?
Identity.
An identity function. Very good, all right? An identity function. And we're not going to work too much with this function in terms of as an identity, but indeed this is the name that we give it, and I may write it, well, let me just repeat that. F of x then is equal to what? F of x is equal to x. Okay? Let's look at a fourth example, and again, let me take a point through the origin, and instead of picking a slope number of 1, let's pick a slope number, say, of 3. Suppose we come out 1 and rise 1, 2, 3, and through these 2 points we have a line, all right? And let's indicate that line as this one that we have right here. And who may write the equation for this line? Ken?
Y equals 3x.
Here we have y is equal to 3x. Now notice there the slope number is 3 and the y-intercept is 0, so we may simply write y is equal to 3x. Now this is an example of a function that in fact we would like to investigate in a little bit more detail today, and it is called the direct variation function, okay? The direct variation function. And instead of calling it a number, a specific number 3, again let's think in terms of a number m, and what then would be a formula for this direct variation function, Chuck?
Y equals mx.
Y is equal to m times x, okay? What I'd like to do is to concentrate a little bit more on this particular function right now, okay? So let's come over here and talk about this, let's think of it in terms of another idea. And suppose I were to write a sentence such as y is directly proportional. Y is directly proportional to x, okay? And here's a sentence in which we may, what I'd like to do is to translate that into an algebraic sentence. Or how about y varies directly as x, okay? Y varies directly as x is another way in which we may say the same statement, the same sentence as y is directly proportional to x. And what I'd like to do is to write an algebraic sentence which describes this phenomenon. So what do you think we may write here for this sentence? And Bob says
Y equals mx.
y is equal to mx. Now notice it says y varies directly as x, in which we have this number m here, and it's given a special name in which we may call it the constant of proportionality, all right? The constant of proportionality, or else some people refer to it as the constant of variation, all right? So every time we have a direct variation, all right, every time in which we want to look at a direct variation, we have to think in terms of this constant m, okay? Let's look at a specific example of this, let's call this idea 1, and let's come up here and look at the second idea in which we have a particular example. If y varies directly as x, and x is equal to 2 and y equals 6, find y when x equals 4. So you say, well, let's see now, the first line says if y varies directly as x, so what then may we write there for a sentence? And what is our sentence, which will interpret an algebraic sentence for this English sentence? And what can we say, Ron?
Y equals mx.
Y is equal to mx, okay? Now, here we have a particular value for x, namely 2, and a particular value of y, namely 6. Rather than looking at those particular numbers, let me now talk about y sub 1 is equal to m times x sub 1, okay? In which I don't have numbers here, but these are some, we may think of them as constants, all right? And suppose we had also y sub 2 is equal to m times x sub 2, all right? Now, let's divide both sides of this equation by x sub 1, and notice we have y sub 1 over x sub 1 is equal to m, all right? And now, let's also do the same thing here. Y sub 2 divided by x sub 2 is equal to m. Now, here we have a number is equal to m, and another number is equal to m, so what is your conclusion about these two numbers? They are, they are equal. What property are we using in order to be able to say that? If A is equal to B, and if C is equal to B, then A is equal to C is the transitive property. Therefore, our conclusion here is what? Y sub 1 is to x sub 1 as y sub 2 is to x sub 2, okay? Now, let's substitute the numbers, the specific numbers that we have in this problem. Give me a number for y sub 1, for example. 6, all right? Give me a number for x sub 1. 2, all right? Now, because x is equal to 2 when y is equal to 6, all right? Those two are certainly paired together as, all right, find y sub 2, well, that's the number that we do not know, when x is equal to what? 4. And of course, everybody will say that what? Y sub 2 must be equal to 12. You say, well, I could have done that in my head anyhow. Let's continue looking at this idea, shall we? In which what I'd like to do is to write down this ratio again, this proportion, in fact, we call it, in which we have y sub 1 is to x sub 1 as y sub 2 is to x sub 2, okay? Now there's another way in which we write this proportion, which perhaps is a little bit out of fashion today, but I think that it's a meaningful way in which we can write it, in which we can say y sub 1 is to x sub 1, now notice our two dots here, our semicolon, as y sub 2 is to x sub 2, okay? Now, notice the two numbers here in the middle, all right? And in fact, because they are in the middle here, we may think of these as the means, all right? And these two elements, these two numbers are out on the ends, and they are in the extreme position, and that's indeed EXTREME. This is a name that we give these two elements, okay? So let me write down our original proportion again. Notice I call this a proportion. Y sub 1 is to x sub 1 as y sub 2 is to x sub 2, all right? Now, when you look at it in this pattern, you lose track of what are the means and what are the extremes, all right? Now, let's, but however, if you come back here and think in terms of x sub 1 and y sub 2, all right, x sub 1 and y sub 2, notice are these two elements that we have here. Let's look at this and decide to multiply both sides of this equation through by some number which is going to get rid of the denominators, all right? So what number can we multiply both sides of this equation through by in order to get rid of x sub 1 and x sub 2? So who would like to say anything about that? Ron? All right, we can multiply both sides by x, in which we then will get rid of this x, certainly, and however, we still will have this x sub 2 on this side. So what number can we multiply both sides through by in order to get rid of x sub 1 and x sub 2? And Steve says? X sub 2. All right, well, if we were to multiply both sides by x sub 2, we still have x sub 1 hanging around. So Ken says?
X sub 1 times x.
All right, let's multiply by x sub 1. Let's actually indicate that. Times x sub 2. All right, I don't have room to write it on this side, so let me write on the right-hand side. X sub 1 times x sub 2. And of course, x sub 1 divided by x sub 1 is a name for 1, so you have left what? X sub 2 times y sub 1. And here, x sub 2 over x sub 2 is a name for 1, so what's left? But let me write this element first, in which you have what? X sub 1 times y sub 2. Is that right? Now, let's come back and write down this ratio again, in which we have y sub 1 is to x sub 1 as y sub 2 is to x sub 2. Now let's look at this product that we have here. All right, and notice here we have x sub 2 times y sub 1. And notice that will be these two elements, and with respect to the words means and extremes, which two are those? Those are the what? They're the extremes. And notice now, this is equal to x sub 1 times y sub 2, which will be these two elements, and those are what? The means. So what is our conclusion as soon as we write this statement? In words, we can say what? That the product of the means is equal to the product of the extremes, all right? And that's one way in which you can look at this statement right here, all right? The product of the means is equal to the product of the extremes, in which we have here the product of the means is equal to the product of the extremes, okay? Let's look at a fourth example. Here we have the weight of a steel beam is directly proportional to its length. If a steel beam 18 feet long weighs 2 tons, how much will a beam 27 feet long weigh? All right? So, now let's come back in terms of our original statement, which says the weight of a steel beam is directly proportional to its length. So let's talk about W for the weight and say L for the length, in which M is again this constant of proportionality. So the first thing that we have to do here is to write down a sentence which will interpret that first English sentence. And what will that sentence be? An algebraic sentence. In terms of W and M and L. What can we say here? Anyone? Ron?
W equals M times L.
W is equal to M times L, in which we say that the weight of the steel beam is directly proportional to its length. Okay? Now, let's go to the subscript notation, in which we have a particular weight. Well, let's call it W sub 2 is to L sub 2 as what? Let's say W sub 1 is to L sub 1. Perhaps I could have written it the other way around first, okay? Now, let's think in terms of, in fact, let's actually turn it around. The first weight is to its length as some other weight is to some other length, okay? Now, let's look at our particular numbers. If a steel beam 18 feet long weighs 2 tons, so let's think in terms of what? W sub 1 is 2, and its length is what? 18 as W sub 2, how much will it weigh? There is some weight of W sub 2 is to its length, which is 27. And of course, right here, you may think in terms of the product of the means is equal to the product of the extremes, okay? And of course, let's see now, 18 is 2 times 9, and 2 over 2 is a name for 1, and 9 will divide 27. Therefore, what is your conclusion about W sub 2? It's equal to 3. All right, so we can say that therefore what? The beam weighs what? The beam weighs what? 3 tons. And I think we can check that. Okay? Now there's one other idea that I think we can look at today. It's not part of this idea of a linear function, but in fact, I think it's an interesting problem that you'll enjoy looking at. So let's do that right now and see what we can say. All right? Now, let's come over here in which, let me call this idea C. Now, what I want to do is to introduce a new notation. Suppose I have something like 3.2, and I'm now talking about the greatest integer of 3.2, which is less than or equal to this number. All right? I want that integer and the greatest integer, which is less than or equal to 3.2. And of course, what is that number? I want the greatest integer, which is less than or equal to 3.2. All right, so it is 3. All right. How about the greatest integer, which is less than or equal to 4.7? And everyone says, what? 4. How about the greatest integer, which is less than or equal to 5.3? Careful. The greatest integer, which is less than or equal to negative 5.3. Think of your number line, and I want the integer, which is negative 6. Okay. How about the greatest integer, which is less than or equal to 3.0? All right, less than or equal to this is indeed the number 3. How about the greatest integer, which is less than or equal to 0? Is the element what? 0. All right, how about the greatest integer, which is less than or equal to 10.9? And what number is this? This is what number? Negative 11. Okay? Now, this is a notation which describes a function which I will write in this pattern with what looks like a bracket notation, but a rather heavy bracket, in which we say that y is equal to the greatest integer of x, where this notation means the greatest integer, okay, the greatest integer less than, or equal to, all right, less than or equal to x, all right? And in fact, the name that we give this is called the greatest integer function. And here's an example of a function that is very unusual, one that I don't think you've ever seen before, but it's sort of a fun thing for us to do. Let's come over here to our coordinate system and see if we can't graph this greatest integer function, okay? Now, let's, for example, what's the greatest integer of 0? 0. What's the greatest integer of a half? Notice here, by the way, I have taken 2 of these squares to be 1 unit. That is, one unit is out here, okay? And then similarly, 1 unit is here. So what is the greatest integer of a half?
1.
Careful. The greatest integer of a half is 0. All right, so this point is still on the graph. All right, what's the greatest integer of a 4? 0. The 3/4? 0, and so on. What's the greatest integer of 1? 1. So this point then jumps up here, and I think you will agree that the graph is going to be all points between where? Between 0, which includes this point, but does not include that point. So let me put an open circle there, but then it does include this point. What's the greatest integer of 1 1/2? 1. What's the greatest integer of 1 3/4? 1. What's the greatest integer of 1 1/4? 1. What's the greatest integer of 2? 2. So that point jumps up here. Is that right? Okay. So we have to have an open circle here, and it's going to be all points on this part of the graph. All right. Now, what's the greatest integer of 2 1/2? 2. Of 3? 3. So that point then has to jump up there. So it's an open circle here, and all points on this part of the graph. Is that right? And I think now you see the pattern. It's going to be all points on this part of the graph, and so on. Now let's come down here in negative direction. All right, what's the greatest integer of negative 1? Negative 1. What's the greatest integer of negative a half? Negative 1. Okay, what's the greatest integer of 0? 0. So right there you need an open circle, and the graph is going to be all points on here. What's the greatest integer of negative 2? Negative 2. All right, what's the greatest integer of negative 1? Negative 1. So I think here we need an open circle, and it's going to be all such points there. What's the greatest integer of negative 3? Negative 3. Is that right? So I think you'll agree that our graph is going to look like this. And like that. Is that right? So notice our graph consists of these steps. They look like steps. So in fact, another name that one gives this kind of a function is called a step function. Okay? Why don't I give you your assignment for next time, and I think that's all that we need to do for today.